Okay, so in this video what we're going to do is run a between subjects Anova and its non-parametric equivalent across global. Again, I'm just going to create a new R script. I'm going to link it. First thing we're going to do is link it to, or first save it. So a shortcut of this is just press Control S or Command S if you're on Mac, and I'm just going to save it as 04 Anova between subjects, or BS, and I'm going to link it to the setup file. So link to our setup file, and again it's the same thing we did in the last few files, just source 01 setup.r. So if I wanted to run this entire script in entirety, I would make sure to run whatever is in 01 setup first. So if I clean this environment, show you again, and I run it, it creates the psycho-df and the well-being df. Okay, so let's run our one-way ANOVA. I won't do a repeated measures ANOVA this week or a factorial ANOVA between subjects. It's fairly straightforward. The package we're using can do, let's say, a factorial ANOVA. I'll just link it in the textbook, and I'll give a guide in the textbook about how to do that. I won't do it in the video. Okay, one-way ANOVA. So the formula for a one-way ANOVA, or the syntax for it, is type in ANOVA. Right, say formula is our we're going to say our dv is predicted. We use tilde by our iv. That's what's going to check. We specify the data set, so our data frame. Homo being homogeneity of variance. Do we want to test for that? We set that to true. If you want to do post, or if we want to specify an effect size, we just type in effect size, and in quotation marks we put in part eta, being part of eta squared. We can put in others, and I'll go through that in a second. If we want to put in a post hoc test, we type in post hoc, and it's a capital H on the post hoc, and we just put in whatever our independent variable here is in quotation marks. If we want post hoc correction, we type in list and we put in whatever corrections we want to put in. We can put in multiple, but in this case just put in Bonferroni. I'll show you in a second where you can find information about the other corrections that you can do. And we might also want post hoc effect size, and here I just put in quotation marks D. So that will give us Cohen's D when it does the post hoc corrections. Okay, so that's the formula. And what I'm going to do is I'm going to copy this, and I'm just going to comment all this out so I don't run it. And to do that I can press Control Shift C, and I'll comment out all our code here, or if it's Command Shift C if you're on Mac. It's just a quick way to comment out multiple lines of code. So I don't want to run this because it will give me an error. Okay, and I'm going to take this and I'm going to run it on our well-being data frame. I'm going to look at well-being based on condition, whether no caffeine, low caffeine, high caffeine. And I'm just changing the variables, right? So I'm going to say I want well-being. We're going to predict well-being based on condition. Our data frame is the well-being data frame. That's where it's going to find these variables. And then just in the post hoc, like if I run this now, it won't run, because in post hoc I just said IV. I have to change it to condition. If I run that now, I'm going to bring this over here and lift this up. We get three tables. The first being the result of the one-way ANOVA, based on condition and residuals. So you get your F statistic, you get your p-value, and you get your partial eta squared. It has the assumption check, homogeneity of variance. If you want to check for normality, check the descriptives video. There's a part on how to do that. If you want to do Shapiro-Wilks or a QQ plot. And in post hoc tests, then it compares each of level of our condition against each other. So high caffeine, low caffeine, high caffeine, no caffeine, and low caffeine, no caffeine. And it gives us the mean difference, the standard error, the degrees of freedom, our test statistic, p-Bonferroni, and our Cohen's d for each comparison. So you get a lot of information there. Okay, so that's like a basic way to run a one-way ANOVA. If you look at the function ANOVA, so if I type in quotation mark and then ANOVA, you'll see, like the descriptives function, there is help section, there's information about how to run it. And you can see that this is all the arguments or all the inputs we can give it. And there's much more than I've put in here. So feel free to kind of have a look through this at your own time. You can also specify different inputs. Like for example, for the effect size, you could do eta squared, part eta, or omega. If you look at sum of squares, you can use different terms here. That'll give you different sums of squares. If you look at post hoc correction, you can use none, you can use Tukey, chef, bon, or home. So there's a multiple set of post hoc corrections you can give, and there's other values you can provide in here as well. So one thing I'm just going to do, I'm just going to add in a QQ plot. So this will do it for the entire well-being column. It doesn't do it based on condition. If you want to do it based on condition, you look in the descriptives. Okay. And it's going to say QQ plot equal to true. If I run that, it gives me the same information here, but it just adds in a QQ plot as well. And that's how you'd run a one-way ANOVA. Okay, so that's the one-way ANOVA. How will we do its equivalent, let's say Kruskal-Wallis. So let's say Kruskal-Wallis. Well, to do that, there is a function called ANOVA NP. I just will put a question mark before it. ANOVA capital NP. And it comes from the same package as ANOVA. It's from the JMV package that we loaded in here. And again, it gives you the uses and all the arguments in there, and the arguments that you can change from false to true, true to false. And it gives an example at the bottom. So the formula for this, I'm just going to take this, the usage, paste it down here, and we can read through it, right? So the data says what data frame we want, so it's the well-being data frame. I'm not actually going to use so I could put in this one's a bit complicated, depths and group. What we can do instead is use the formula function, or formula argument. Take formula, and again it's our IV, or DV predicted by our IV. ES provides effect sizes, I'm going to say true. And pairs, whether to do pairwise comparison, I'm also going to do true. So that would be a straightforward way to run a Kruskal-Wallis. Or actually, let's just say this is the syntax, data equal our data frame. I'm going to copy this and just comment this out. And in this case, I'm just going to put in well-being underscore df, and our formula being well-being, or we'll do a different one. We'll look at, say, well-being, we'll look at depression based on, again, condition. And if I run this, it just might take a couple of seconds. It gives me the non-parametric version of Kruskal-Wallis. So if we haven't met our assumptions, it gives me depression, it gives me my statistics, x squared, df, p, and the effect size, and it gives me the pairwise comparison the Dwell-Steele Quiltrod-Figner pairwise comparison for each group, and it gives me the test statistic and the p-value. So that's how you'd run a Kruskal-Wallis and a one-way between subjects ANOVA. In the textbook, I'll also give links about how you would do a factorial ANOVA or two-way or three-way ANOVA, but that's how you do just the one-way. Okay, in the next video, what we're going to look at is we're going to look at running a correlation and a partial correlation.